I'm actually one of the co-founders, and even though I have a computer science degree, I'm actually the least technical person on our team. And so this is a bit of a challenge for me to talk about the technical side of our protocol. And it's actually one of the core features that enables us to build some amazing use cases which have never been seen in industry. So it's going to be slightly half technical and half use case oriented. So I'm very much a kind of developer who believes that there's no point developing anything unless it has a use case. And particularly in the blockchain industry, we all get criticized that we're building tech that has no use case. So we want to share with you a case study, our own case study of something which we think is potentially quite revolutionary. So I'm actually going to focus a little bit quite closely on new application of zero-knowledge technology, which is going to be in the security space. And it doesn't really get much attention because it's very new. All the attention you got so far is on scalability. So ZKEX, Starkware, and Scroll, and all those guys are doing some amazing things with scalability, but there's actually some new applications with security, which I personally believe, and our team believes, is a more fundamental problem. Because if something is not safe and secure, don't really care what network it's actually sitting on. What they want is to have an asset, whether it's NFT or a piece of crypto or something else. They want to do something with it. And sometimes the work is quite passive. It might be staking or holding an NFT, or it might be quite active. So trading assets or playing a game. But the ultimate use case that people are looking for is people are looking to make money. And our job as builders is to make it easy for them. So if you have assets on one chain and you spot an arbitrage opportunity on another chain, let's say a new meme token came up on Solana, which you want to buy, then you've either got to move your money, or you need to use a trusted third party, like a ZKEX, to leverage your original assets. Let's say you've got USDT, to buy the assets on another chain. Now, a ZKEX makes it easy because they take away that complexity, but if you do it in a decentralized way, you have to use bridges. Unfortunately, moving your assets using a bridge currently is quite expensive, it's complicated, time-consuming, and that's why 99% of people are using ZKEXs and CeFi. Point of view, they don't want to lose the users and they don't want to lose the assets to drain out of their network or their chain. They actually try to hold the user and the money in their network and force you to make it difficult for you to move out. And the bigger reason, though, actually is, as an industry, we are going through a massive diversion of different ideas and different technologies, and maybe in 5 or 10 years, some of those ideas will be proven to be wrong or not as strong, and the stronger ideas will come forth. So there will be like divergence, so many different L2s, right? So many L1s, so many different consensus ideas or architecture ideas, but in 5 or 10 years, some of these chains and L2s will die, and we'll have less, and we'll have convergence. So we, as developers, can use ZK technology to force interoperability between these different chains and networks. Since they're not going to do it themselves, we can do it for them. And we have to do it to the point where the security is taken for granted. Now, I have a point of view that there's two things here. One is multi-chain and one is cross-chain. The idea of multi-chain is that you have the same app connected to multiple chains, and the user doesn't really care about the underlying chain. They just care about the asset. Whether it's sitting on Polygon or ETH or Solana, the user doesn't really care that much. But cross-chain is something different. When you actually need a utility on a chain, which is unique. So it might be a gamified project is on BNB chain, and you have a version of your app on that chain. It might be slightly different, and then you move your assets across so you can use it natively on that chain. So actually, both multi-chain and cross-chain are valid case studies, but they're different. Now, I want to go very, very quickly to, I don't think everyone here is an expert in ZK, honestly speaking. So I want to define what a ZK snark is, because it's important for what I'm about to tell you later on. The point about ZK snark is that there's 2 points. The first is that you have a proof system. Basically, it's a very, very small proof system. And we call this the snark, not the ZK, but the snark bit. And what it allows you to do is it basically allows you have a prover who's on this left-hand side to convince a verifier on the right-hand side of something, that something is true. And the amazing thing is, no matter how complicated this secret is, it could be hugely complicated, but the actual proof that comes out of it, that the prover generates, is tiny, is very, very small. So you can have like extremely, extremely complicated calculations and mathematics going on, but the proof itself is tiny, and which is quite an amazing thing. So unfortunately, the prover has to have a very, very powerful computer, a lot of computation power to actually create that succinct proof. However, once it's made, it's really, really quick and fast to prove that it's correct. And the verifier on the right-hand side just checks the proof very fast and very quickly, and if it's okay, thumbs up, can continue. So just for proving that a certain computation ran correctly, when you add in the ZK side, zero knowledge, it means that you want to prove that something worked correctly, but we also want it with zero knowledge, which means that we want to prove it's correct, but we don't want to give any information about what happened in the secret. So the point here is the proof is tiny. So the second point is that the prover is, when the prover wants to prove that statement is correct, then there's going to be a single prover, usually in most cases. And a lot of people criticize ZK projects, saying that, oh, you have a single prover, which is centralized, doing the mathematics. And there are ways around this, but essentially you can have like collaborative proofs. But to be honest, even if, I'll be honest, in ZKEX we have a centralized prover. However, this centralization isn't as bad as you think, because unlike a consensus system, which might be controlled by a single entity, then the worst thing that a prover can do is just to is that they have to follow they have to follow the mechanism that's built inside it. So either they prove something or they don't prove something. It's as simple as that. So the amount of damage that can be done is not the same as, for example, a multi-sig bridge or something, where they could potentially change the direction of assets and things like that. It's a very, very simple and very kind of like innocent kind of centralization, but you can decentralize it. This is the point. But the point here is that the amount of decentralization here is to protect the asset and to make it secret. So it's kind of decentralized in that sense, but the actual architecture itself is like, it's definitely magnitude is more stronger than say a multi-sig bridge or something like that. It's very, very powerful. Now this is a really simple view of what cross-chain looks like. So cross-chain protocols, basically they coordinate the state change. So what happened on the source chain and what happened on the destination chain. And so the core security properties of a cross-chain protocol is that the state communicated from one network to another is valid and final in the source network. And the cross-chain state communication is communicated in a timely manner, as quickly as possible, basically. So you have message-based token bridges. So they're the bridges which allow liquidity flow via messaging across chains. And they typically allow for the minting of assets on the destination chain. So you have the lock and mint. So you have to lock and burn the original asset, and then you mint one on the destination one. Then you have a liquidity network, which is one level above. And this is when you move already minted assets from chain to chain. So they allow users to move assets to other chains, assuming that the asset already is a valid asset on the destination chain, using a message bridge, basically. So the message bridge is like a cross-chain messaging protocol on a very low level. It's not only for asset transfer, but it could be any kind of messaging whatsoever. So there's actually 4 kinds of risk when it comes to cross-chain. So there's network, architecture, implementation, and operational. And I would say the most fundamental one is the network risk at the top, because earlier on I just defined what it is about the core property of a cross-chain protocol. Essentially, by having a cross-chain protocol, you have to coordinate exchange between different networks, and we're making a fundamental assumption about the soundness and the safety and the liveness of the network itself. And next, below that, we have architecture risks, which is basically the design of the protocol itself. And different protocols have different security models, they have different trade-offs and different assumptions as well. And then these are sources or risks themselves that if something was not correct, it could be, all these risks have to be considered and mitigated. So following that is implementation risk, and a simple way to think this is about the code itself. So if you have a bug in your code, it could actually lead to a massive hole in your protocol. It's very common. And so any kind of risk that stem from this kind of creation of this kind of code is related to the a vulnerability in the protocol itself. And the very last thing at the bottom is the operational risk, which is basically risks that stem from how these protocols are operated and managed. And typically, the protocols involve a number of different moving pieces managed by different people or different kind of pieces of code. So there's a huge, massive surface that things can go wrong while the bridge is alive. So I'm very keen on the time. It's already 44. So I'm going to skip forward a little bit, and I want to go forward to the different kinds of bridges. And the first kinds of bridge that I want to talk about is a trusted architecture. So the worst one, the most extreme, is on the top left, which is basically having an external validator. And this is, for example, what you might have this for a central government kind of issued kind of token where you have the trusted intermediary. They can say yes or no to you. They can censor transactions. They monitor everything. So this is the worst possible kind of bridge that you can have. But unfortunately, they're actually coming soon. All the governments that want to implement this kind of crypto. But this is the worst kind, essentially, the most extreme. And on the right-hand side, as we become more decentralized, we have the external validator set bridge. So what you see here is that we have, the idea is similar, a little bit similar to the first one, but we have a set of parties, typically a multi-sig, that attest to the validity of the state of both sides. And those parties and the mechanism they use amongst them use basically an honest majority. So if you have like 5 people signing up to agree on something, then as long as the majority say yes, then it will go ahead. You know that this is flawed. Lots of bridges have been taking advantage of this model. When somebody can mimic one of those parties, then it can go really bad. Then at the bottom we have something called optimistic bridge. This is actually even more decentralized as well. So I don't like to call it it's very, very trusted. It's still quite decentralized. And essentially it's quite similar to an optimistic rollup where it relies on an optimistic mechanism with fraud windows to essentially resolve any kind of dispute about the validity of state. And by default it says that, yeah, something is valid until it's proven that it's not. So the difference between the external validator bridge and optimistic bridge is that optimistic bridges, they make the honest minority assumption as opposed to the honest majority assumption of validating set bridge. Now we move to trustless bridges. And one of the most secure models would be a state validating bridge at the top. So in this case, we have a destination network, and let's say network B that receives state from network A validates the state transaction corresponding to that state and independently verifies that any state it receives is verified to the rules within that protocol. So basically that means that this is a really good example of a rollup, say a ZK rollup inside Ethereum. So it doesn't have a different security mechanism. It has the same as it inherits the same security as Ethereum. So this is actually very, very secure. So you can be quite assured that ZK rollups are very, very secure because they inherit the same as Ethereum. And so over here, it's essentially we can categorize this as consensus verifying. So bridges in here are basically bridges are what each network they're doing is not really they're not really kind of validating state or state transition, but rather at a high level they verify that consensus has been achieved in any block that it receives. So basically in this scenario, network essentially kind of relay blocks amongst each other. Sorry, I'm actually talking about the second one. Sorry, apologies. So the consensus verifying bridges, okay. So in this scenario, networks essentially kind of relay blocks amongst each other through the help of intermediaries. And each network can independently verify whether the block it received or the block header that it's received has a valid consensus according to the consensus rules. So IBC on Cosmos is a really good example. And this is considered to be a really secure method as well. And the question that people have is, why can't we build this in Ethereum? And the thing is that IBC is a really elegant solution to cross-chain communication problem. So you run a light client for the source chain A on say a target source chain B, and that light client running on the destination chain verifies consensus of the original chain and keeps track of the original chain header. The problem with IBC this kind of consensus Lightbridge client, the IBC type mechanism on Ethereum is that Ethereum computational environment is too expensive, very expensive in terms of gas, to verify the other chain's consensus, especially if the other chain is non-EVM. So bridging from Ethereum to other chains also has problems. So keeping a track of Ethereum's very large validated set and the corresponding public key and stake distribution is quite burdensome. It's a pain in the butt, not really possible to build. So the solution that people have come up with, I would say in the last 1 year, is ZK Bridge. Most people haven't really heard about it, but actually this is quite beautiful, quite elegant, in that it's a variation of the client bridge. However, what we have is, the idea here is instead of having each network verifying the consensus of another network, can be quite expensive, we do it off-chain, and we use validity proofs that are sent to the networks themselves. So essentially, ZK bridges use ZK proofs to make the verifying consensus more efficient, in the same way that we use ZK snarks to help ZK rollup teams scale execution. So now we're able to use the same idea, but for bridging here as well. So it's fast and very efficient. So there are actually 4 cool projects which I like, which I follow. The first is Succinct. The second is Electron Labs. Electron Labs is interesting because they actually had the idea to rebuild IBC in Ethereum, but it's a similar kind of idea as Succinct. And we also have literally called ZK Bridge project. I think it's called run by a company called Polyhydra or something like that. And we have a 4th interesting variation. It's not strictly speaking a bridge, but it has a multi-chain rollup, which is ZK Link. So ZK Link is, I think, the only multi-chain ZK rollup in industry right now. There's another one, but they're not really, haven't really made it yet. They're still in beta. But ZK Link is pretty much ready to go live. So we have this new ZK interoperability standards, and I personally think that over time this will become the standard because they are not assuming inherently, like other bridges are secure, but they use game theory to be secure, while ZK uses mathematical verification to be secure, which is just better. It's just better. Not to say the other ones are bad, but this is just better and potentially much faster. The problem right now, though, is computationally ZK is very expensive. But again, with time, this will get a lot faster, a lot better. So to go through a really quick example, we ZKEX are using ZK Link. For several reasons, because actually they were one of the first protocols to actually have a working API we could integrate into and start using. These other 3 protocols came a bit later. And what we like about this is the ability to have multi-chain as default, be able to use, so people can use their assets on one chain and buy and sell other assets on other chains, which is quite revolutionary in industry. So there's basically 3 stages in a classic ZK rollup solution. Number 1 is when you have a commit stage, you have a proof stage, and also you have an execution stage. However, the interesting thing about multi-chain ZK rollup is you have a new stage called consensus, and this is essentially where you have a Oracle network, a third-party Oracle network, process the stage where it basically accomplishes the interchange of a final root of each chain. So you have essentially a recursive proof. So on chain A, you generate a final root. On chain B, you generate a final root. And then you have a recursive proof that is checked by the Oracle. So these basically, you have like 2 systems that have both networks have a mutual final root. So it's very easy to check whether or not the cross-chain transfer was valid or not. So if it is valid, then essentially the Oracle uploads the transaction parameters and the final root to the layer 1 for settlement, and it's settled. So in this way, you are mathematically verifying cross-chain transfers in a way that hasn't been done before. So you essentially have a check and balance security design. The cross-chain transactions are verified with ZK snarks. They generate the final roots. And then the Oracle network, which is basically independent layer of group of juries, and we are using layer 0 as that independent network. And so they are the ones who check the final roots from chain to chain and compare the final roots to make sure they're consistent. And so this is separating the verification and the judgment. So we have 2 networks. So if somebody wants to hack us, they need to hack ZK's link, and they have to hack layer 0. So I think it's not really possible. So we think we are very, very secure in terms of bulletproof security for any asset, on the multi-chain asset. I don't think any other bridge can say this. They always have, I think, some kind of compromise somewhere. I don't think we have any compromise in comparison. So we have even we can't rug our own customers, to be honest. We have no idea what's happening either as well. We just know that it's going okay. And if something was to happen in the middle, maybe the sequencer gets corrupted or something like that, the worst case scenario is it rolls back. So I want to summarize what I just said with a little bit of a metaphor. I like metaphors and analogies. So if you imagine that current bridges are like pots of gold and like cash and jewelry sitting in the middle of the town, the city center, and you have security guards standing around all this money and assets, and you just hope that the security guard doesn't fall asleep or he's not corrupted. You have to trust that the security guard will do his job to protect the assets. But on the ZK, using the ZK technology, instead of what we have is we have a bulletproof glass house that's protecting all the assets. So only you are the one to get the key, and only you can get to your locker and extract your money. No one else has your key. No one else can actually access that money, but it's all transparent. At the same time, it is transparent. ZKEX, on the other hand, is a black box. You have no idea what they're doing with the money that's sitting in there. You don't even know if there's any money in there. It might be empty. We saw this with FTX. There was no money in there, actually. No assets. They stole it. But with ZK, essentially, we have a transparent box, which is pretty much bulletproof. So at the very beginning of my talk, I mentioned that 99% of people are using CeFi. It's because ultimately asset diversification is very important. We should not stop people from trading what they want to do. We should not stop them. We should enable them. So if you make it difficult for people to take advantage of opportunities to make money, then activity will drop on your network eventually. And eventually the network effect of crypto is less people are active in crypto, the worse and worse and worse it gets for us. And everything might even collapse eventually if it's bad enough. So the source of assets from multiple chains must be maximized. We must maximize activity as much as possible. We shouldn't be too kind of stuck in terms of methodologies. We just must enable users to do what they want to do, especially outside of Ethereum as well. So if you want to access assets from multiple chains, then cross-chain bridges are the first solution that people think of. But they're also the first problems that we have with security as well. And if deposits are implemented on cross-chain bridges, then there will be problems. $2.5 billion last year, and we don't know how many this year. There are hacks going on every single day pretty much. And plus the usability aspect as well is very, very painful. Right, so with ZK technology, essentially we can deploy to multiple chains on Ethereum, all the ZK rollups, Polygon, Avalanche, ZK Sync, Startnet, Scroll, and others. And it natively supports trading tokens on all these chains without needing any bridge whatsoever. So the way it works is you have complete reassurance that you can lock your assets on your wallet and then use it as collateral to trade on ZKEX with the reassurance that no one else has access to the asset. So, that essentially that glass house analogy is basically gets even better, because if you have a sequencer, then inside you can actually see it. You can actually watch that sequencer, and if you don't trust that sequencer, you can even have a watcher outside the glass box, and those can be independent third-party oracles. And even, for example, if you're a market maker firm and you didn't trust what was happening inside, you can still watch it. So to be a witness is very cheap and very simple. So you have complete reassurance that everything's secure and everything is safe. So I was actually going to tell you, my time is up. I was going to tell you that actually we are the first DEX to have portfolio margin. Ask me in person what that means. Very low entry for retail users and also pro traders. And there's no cross-chain risk whatsoever. You can buy and sell any token using any asset whatsoever. You have token merge as well. All your assets are aggregated on ZKEX. Very, very cheap, very fast, very easy, blah, blah, blah. But actually what I want to say is we're going to rug pull our users next month, because people think that we are actually secretly CEX when we actually are DEX. So to prove it, we're going to shut off our sequencer for 3 days, shut down our network, and we're going to post like memes of us sitting on the beach with like we stole your money. But actually users can actually connect to a recovery node and get their money back. So we're going to prove to people that actually we are not centralized. We're not custodial of your money whatsoever. So any money you got ZKEX anytime whatsoever, even if we turn it off right now, we turn it off and run away, no, it's okay, your money's safe. You can get it back on chain it will rebuild, and the ZK proof will be generated, and it will come back to your wallet within about half an hour. So you're completely safe. So that's what I was going to say. I'm here to tell you that we're going to rug pull you very soon. So yeah, thank you so much for your time.
So thank you for Balal for your great talk. So we can have one question. Anyone? Okay.
I hope I didn't scare anyone. I was only joking. It's a fake rug pull, not a real one. So don't scare anyone. Okay, thank you though. Cheers. Thanks.
Okay. All right. So all the sessions on the day one are over. So thanks for coming, and I hope you all learned a lot today. And we will publish the recording to the YouTube and ensure you can watch the talk again. And in the evening, we have a lot of side events, and then you can find the information on the website. And last, please remember to bring your badge and the ticket tomorrow to ensure that you can get into the venue. Thanks.